Hello everyone, my name is Olga and today I'm going to talk about predicting property attributes in real time with multimodal AI on Google Cloud. Uh, just a sec, sorry. Okay, it doesn't work. Okay, cool, it's okay. Sorry, okay. I will start by walking you through the challenge we set out to solve. I'm going to talk today about how we prepare the data, how we decide to build our own model, why we decided to build our own model. I'm going to talk about how we evaluated that model, and after all, I'm going to share with you how we integrated that into real system for real-time use, and I will wrap it up with key takeaways from the project. So to explain you the challenge, I will start by a very simple quiz. So look at this photo. Can you spot a swimming pool here? I think it's very easy, right? Everyone can see that blue thing in the middle, and that's definitely a swimming pool, and so can our AI model. So meet GLAD, and GLAD stands for Great Listing Attribute Detection. And that was simple, but let me ask you another question. So what kind of swimming pool is this one? Is it a gas-heated swimming pool, regular swimming pool, solar-heated swimming pool? It's not obvious from the image itself, but if I show you the text and if I'll give you a couple of minutes to read, you will find the answer. It's actually solar-heated swimming pool. So this is the first key insight. Sometimes to capture some more sophisticated details about properties, one data type is not enough. And that's why we built a new iteration of GLAD model. So meet GLAD 2.1. This is multimodal AI model that we built at REA, and it detects highly sophisticated, non-trivial property attributes in real time. So today I'm going to show you how we build it, how we deployed it. We're using Google Cloud for that, and we use it in real time. So I hope you're going to enjoy it. To set up to start from goals, we set up two very simple goals. We wanted to detect more than 70 non-trivial property attributes. And when I say property attributes, I mean features like solar heated swimming pool, marble bench top, dishwasher, things that we are actually looking at when we're looking for a property. And the second goal is with almost 2 million daily unique user and 1,000 of new listing coming through every day, we wanted to deploy it in real time. So let me walk you through real-world impacts that those goals are actually unlocking. We identify multiple use cases. Obviously, when you're looking for a new property, let's say you're looking at a beautiful kitchen, the things that you don't really see is whether it has a gas cooktop, whether it has a dishwasher, and all those small details can actually make or break your decision. So this is where our GLAD model excels. It automatically detects all those hidden details. But the impact goes beyond just showing more information. For our environmentally conscious user, they can find those details that matter for them, like solar panels or some more efficient supplies. Then people with some accessibility needs can find features that are very useful for them. And that's not just about showing more information. Those attributes can actually enhance our AI search experience. So attributes can go and improve our property price prediction models. And those features can be used for our personalization programs and improve our recommendation system with additional features. So there are multiple use cases, and it's actually, it helps us in a lot of fronts. So to just sum it up, we frame this task as multi-label classification. So for each pairs of images and text, our model could detect multiple labels. So here, for example, there you can see that the labels are open plan, stone bench top, walk-in pantry. So this is kind of things that we built our model to detect. So now that we know our problem and now we know our goal, let's set the next question, how to build it. And even more fundamental question is, do we really need to train it ourselves, or do we want to use third-party API? So we made this choice over 1 year ago, which is practically an anxious time in AI history. And with today's rapid advancement, we probably might decide differently. But let me walk you through the reasonings we had back then. So we had three fundamental requirements. We wanted something super fast and super accurate, and we definitely had our computational budget. Nothing of the shelf worked perfectly, and back then VLM models were great at accuracy, but they didn't meet our latency requirements, and that's why we decided, and we cared actually most about speed and accuracy, and that's why we actually decided to build our own model and host it on Google Cloud. So that gave us very light, very small model that was that was trained on specific use case, so we could control accuracy, and we are not depending on any external API, which is also awesome. So that was reasoning almost 1 year ago. Since we now know that we want to train our own model, training starts obviously from having a right data set. And in our case, we have highly diversity of attributes, and we need to have a good amount of every attributes presented in our data set. So we started with a simple assumption. If the text has lots of attributes, probably images will also have lots of those attributes. So we focused on text to detect good candidates for our data set. So we created a list of attributes, and then we created a synonyms, every possible way that those attributes can be detected in text. Then we use SQL with regex to actually go and highlight all those attributes in text. So once we made it, we had our pool of candidates, and then we sampled. And we sampled with several things in mind. We wanted to have enough examples of every attribute. We wanted to maximize number of attributes per listing, and we still wanted to have a good diversity of different properties. So we wanted properties in different range, different locations, and we wanted property with different kind of types. So it can be units, houses, and other things. So the final data set had 25K listings, and we had almost 500,000 of images, which is a big number, I guess. So we split it into training, validation, and test. So training obviously was used for training purpose. Test was used for validation, was for hyperparameter tuning, and then we had a test set. And apart from that, we also had a tiny set, which is our holdout set. So that set was selected in very unbiased way to actually have as close to real world distribution data as possible. And that was a data set that we used to actually select our final best performing model on. Raw data is obviously not enough. So since we know that we're training model, we have our data, we need to have a great labels. We need to have a great ground truth. So our model needs to know what we're trying to learn. And since I said to you that it's actually a big data set, we couldn't manually label it, obviously. So we used a bit of help from AI. So we built a model labeling pipeline, which is label modeling pipeline, which is model agnostic, and is scalable, reusable, so we use it for several use cases. So the data comes, so we first start from pydantic model, where we find clearly every attribute we're trying to detect. Also have a prompt, and we pair it with a data set. So data set comes in batches, so we have batches of images and text. Labeling was happening for us with GPT-4. Back then, that was our model of choice, but obviously we could decide differently today. And everything was orchestrated by Argo workflows, and it was running on GKE. So it was scalable, reusable, and very easy to set up. And a final labels lived on Google Cloud Storage. So the result was a clean, ready-to-use dataset for model training. And once we generated, we could extend it anytime if we needed for more attributes. So with label data ready, we know we're trying to build our own model. We need to have a good model architecture. So the idea behind this model is very simple. Think about how how we are comprehending details. So we use different senses, and this is the same idea for multimodal models. So our model actually use both text and images, and they both go through its own specialized encoders. So those encoders turn those data types into embeddings, and embeddings captures the essential meaning behind all those features. So those embeddings are numerical representation of that, both images and text, and that's what model can actually learn from and understand. So then instead of keeping those things separately, we actually fuse them together. So we use a simple concatenation. And this is one nice learning. We thought that we might try so many different other way of concatenating those embeddings, but in our case, just simple fusion was good enough. And then those combined representation goes into combined heads. So this is a classification, vanilla neural networks. This is where model actually learns to pair those things like a text and visual evidence. So if your text saying marble benchtop, this is where model actually learns to pair it with a visual evidence in the image. So the last layer is prediction layer, and this is our layer with probabilities. It gives us for every possible attribute we want to detect, it gives us how model is confident about that particular attribute to be present in this particular image and text pair. So this is our model architecture, and yes, you can see it's pretty simple and it worked really well for us. And it can detect more than 70 attributes right now. So architecture is done, we have our data, the next step to train the model. So the training pipeline also reusable, and we also reuse it for many other use cases, and it starts with label data. So label data I shared with you before, it lives in Google Cloud Storage. And then we also paired with some pre-trained encoders from Hugging Face. So this is where we don't want to start from scratch. We use a head start with Hugging Face models, but we still fine-tune those embeddings, and we still fine-tune combined head. But this is where we start from. And the training happens with PyTorch Lighting. So that framework helped us keep code modular and reproducible. It also gave us lots of additional features that PyTorch didn't have. And by training, we actually log all our metrics and weights and biases, and the final model went to Google Cloud model registry, ready for serving or ready for further pre-tuning. And I think I forgot to say that the training was done on Kubernetes and orchestrated by Argo workflows. So we could scale up large batches without manually managing any jobs or workflows. So training gave us a good start, but it's not enough. We need to spend some time on experiments. And we ran about 250 experiments to get GLAD right. And we covered multiple fronts. So we tested different architectural tweaks. We tested different way of implementing loss function. We tested different way of concatenating those embeddings. We played around with attention layers and attention mechanism. We also invested heavily on selecting the right image and text pre-trained encoders. Our selection criteria were very simple. We wanted something small, something efficient, something trained on very well-known curated data set, and something proven on like a industry standard benchmarks. Apart from that, we also tried to squeeze every bit of performance during hyperparameter tuning, playing with batch sizes, playing with different dropouts, implementation, and normalization layers. And finally, since I already shared that our data is very diverse and there are so many attributes, that's why we played with data manipulation techniques. So we played with down and up sampling because those some attributes are obviously more rare than other, and that down and up sampling gave us a good results actually. We also played with data augmentation. So we tracked everything on weights and bias for training and testing. So weights and biases gave us opportunity to actually track so many things like loss function, all metrics we cared about. But the final model was selected with a Tableau dashboard, and the final model was selected based on tiny set, which is our holdout set. And the Tableau dashboard wasn't that easy to actually set up, and we made it on purpose because we didn't want to be biased. We didn't want to check every model on our holdout set. So that required additional steps, and that what actually we made up on purpose to have like a higher level entry, to not to be very tempting to actually check every model and hold out. So once we had the strong performance and once we know that, okay, we have something to test, we needed to have some sort of framework to select the final model. And since I already shared with you that this is the classification problem, I'm not going to surprise you. We use a very simple classification metrics like precision and recall. So precision is about being correct when we make predictions, and recall is about catching as many true cases as possible. And to illustrate that, I'm going to run you through a very toy example. So let's say we have an image and text. We know that the model is supposed to detect open plants, done bench top, and walk-in pantry. But for some reason, model detects additional attribute, which is hydronic heating, and it's not there. So precision will be 75% because model actually detects something incorrectly, but recall is 100% because all relevant cases were detected. And because of that, we actually cared more about precision. So making a wrong prediction is worse than actually not predicting something. We didn't want to make our users suffer by looking at some obvious things and think like, why did you detect that? So we wanted to avoid that. That's why precision was our #1 evaluation metrics. But we mostly cared about 4 different variations of those metrics. So first one was average precision of a given model. We wanted some model with a good overall accuracy. We wanted precision per attribute, so we wanted the model to be consistently good for different features, different attributes. We also decided that we want to maximize the number of attributes that model can predict with more than 80% of confidence, because we obviously wanted our model to be as good as possible across all the attributes. And we still cared about recall, so we set up some minimum recall that was required for the model to be viable and to be considered having a good coverage. So that was our model. We selected our final model that met all those thresholds and was just the best performing one. And the question next is, how do we deploy it in production to actually serve real-time traffic? And our architecture is event-driven scalable. So the final model lives on Vertex AI and Foyin, where Google actually provides GPU for fast inference for us. And here how it works. So we utilize Google PubSub, and this is a messaging service that lets the system to pull and push messages without them being correctly connected. And events flowing into PubSub input topic. So everything like a new listing or new image, those kind of things can trigger the event. So we got our messages into input topic. And then our orchestrator is running on Kubernetes, and that handles processing with 3 key components. So we start with subscriber. Subscriber pulls those messages in. Then the processor calls Vertex AI and goes all those predictions, and it sends back to publisher. And publisher actually publish all those final enriched attributes to our PubSub output topic. And the beauty of the system is in loose coupling. So downstream tip doesn't need to know anything about model inference. They're just consuming our messages. And everything runs containerized on Kubernetes, and it deploys through Argo CD, giving us reliable, scalable, healthy system with 0 downtime deployment. So the event-driven architecture we used actually helped us serve thousands of predictions in real time. And it was also very easy to integrate with current REA infrastructure. So let me walk you through some final results. And I'm pretty sure if you're using REA and if you're looking for a property, you saw lots of those examples, but here are a couple more. So here, for example, you can see an image, and this is like a building, and you can't really see a solar heated pool. Oh, sorry, still focused on a solar heated pool. So you can't really see a solar panel system, but it's clearly should be somewhere there because this is a building outside picture, and the text actually detects that. So you can see those detected attributes below. And here is one more example. You can see a beautiful kitchen. You can't really see if it has a stone bench top or those ducted air conditioning system, but the text confirms that those attributes are here. So the user doesn't need to go and look closer. It's already detected and highlighted. So that's how we build our model in real time, and that's how the model detects attributes right now. And I'm gonna share with you some key takeaways. So the first things, we couldn't detect so many attributes, and we couldn't do that just by using one single data type. So definitely multimodal beats single model. Another thing is start simple, iterate fast. So it's very tempting to actually use and start building something very sophisticated and complicated. And we started our process by listing all those possible architecture we could have. But in our case, the simplest one works the best. So you don't need to spend all your time actually playing around with sophisticated architecture sometimes. Yeah. And the next thing is probably it's good idea still to prototype with APIs. And if those already built-in solutions doesn't meet your requirements, which are for us, our case was actually cost, speed, and quality, then probably building your own model is solution. But I'm pretty sure it's gonna change since third-party APIs are great enough right now, and it's not a good idea to reinvent the wheel. And the final thing is design for production from day one. So we built that event-driven architecture using GCP, and it worked really well. And we now have 3 more processors that follow the same pattern. We love it a lot. And we now think that we now need to invest time in actually making more modularized and plug in. So we don't need to duplicate lots of code because lots of parts are actually reusable. So those are our key takeaways. Thanks a lot for your attention.
Thank you, Olga. Time for questions.
Hey, thanks for the great presentation. You mentioned that you would have done things differently today. What would you do different?
So when I was saying that we would do things differently, I think 2 things. We would test one more time if ready, like off-the-shelf solutions are good enough to actually just outsource it. And second thing, we would plan our PubSub GKey system to actually be reusable as much as possible, so we don't need to duplicate those processors. Yeah.
Ooh, thank you.
Thanks for the presentation. Did you estimate the accuracy of your labeling pipeline? Given that it uses GPT-4, it might make mistakes.
So we spent some time actually making sure that we minimize our mistakes. So we spent some time working on prompt. Obviously, we had we labeled some set of pairs of images and text manually, and then we took time to evaluate if GPT-4 is working, which prompt is working. So basically, prompt engineering. And once we labeled that, we randomly checked labels, so we still had human in loop component. Yeah.
Thanks.
Thanks for your talk. Correct me if I'm wrong. You used GPT-4 to make labels, and then in your model, do you use the same text and photos to predict the same labels, or you use photos only to predict the labels?
So yeah, so the model has 2 components, image and text. We had image and text pair and labels for our labeling, and then in real time, the real model also use image and text to detect all those attributes. So that's why we call it multimodal.
Thanks. And also, like, did you consider using videos? Because sometimes not only text and photos available.
Yeah, it will be next step or next exploration. Definitely something that we keep in mind.
Thanks.
Just one sec. So there was a video things. Not every listing will have video, but every listing will also have images. That's why that was a more natural decision. Yeah.
question regarding images. Did you have encountered the bad quality of images and how you handled it?
Can you repeat bad?
The bad qualities of the images, like not all the images provided, I believe, are ideal for
Yeah.
detection.
So we focus mostly on selecting the listing with a more rich data, like a data description as possible. So we focus on text. And obviously there are some images with less attributes, but we still want our model to be able to, detect things even if the images are not that great. So we made sure that we have enough representation of different kind of images and different kind of listings and different kind of text. But yeah, obviously some images will be worse than other, but I think on average, we have some requirements for the quality of images that people are uploading, so they're not that bad.
Hi, thanks for the talk. Now that your model's live and it's like in production and working, do you guys have a system in place to handle and manage like model drift and evaluations?
This is something that we're working on. Yeah.
Cool. Any more questions?
Hi, thanks for the talk. I'm really appreciate it and learn a lot. So I saw inside the training pipeline, we have introduced Argo workflow to orchestrate the training step. Can you share some benefit of Argo workflow bring into the training pipeline? Because I also know that there's some sorts of like full stack orchestration out there like Qflow and then smaller component of it. But I see we select Argo workflow. Can you share some benefit of Argo workflow?
Yeah, so we use Argo workflows to orchestrate our Kubernetes and deployment. I not really like. I mean, that was a natural choice for us, and I think we used it for other several like products that were built before. So we already had some learnings and understanding, and we already had our how we call it? I forgot. So that was something that was that easy to use because we already had several products that are being run with Argo workflows on GKEs. That's why we selected that as our choice. But we're happy with that because it's easy to maintain and it's something that we never had any issue with. And so once, for example, we had some issue with increased traffic, you can easily auto-scale it. So that's great. That worked for us.
Thanks for the talk. I was wondering if you had like kind of additional data labeling efforts, like examples would be take an image, come up with like a really specific brand that's in the image. It could be image to actually describing property, like, so some custom data labeling efforts have you worked on?
So the way how we did that, we had a prompt. We spent some time creating a good prompt. But the way how we deal with all those attributes, we have a pydantic model. So that model has a clear definition of every attribute that we want to detect. The additional thing we did that we found that sometimes models mislead something. So for example, dishwasher and oven, that looks very similar. We didn't want to, the product people didn't want us to highlight oven, but we clearly saw that model wants to detect oven. So we add that attribute as additional one, but we don't publish it. So that's was our trick to actually make the model works a bit easier. Not sure if that answered your question.
Anybody else?
You mentioned that you optimize for speed and accuracy. What's the speed of the model? How fast is it?
It's a couple sub-seconds, I think, per response.
Would you replace this model with GPT for 1 minute today or for 1 nano? Do you evaluate?
I mean, that would require some additional testing and playing, but given that the model already is there and is good enough, I don't think it makes sense to spend money on calling GPT. Yeah.
Thanks.
Any more questions? Okay. That was a very, very interactive session. Thank you all for
Thank you.
questions.